So I want to start by saying something that's probably obvious, and that is that language is a very powerful tool. Using language, we can tell each other anything, from why giraffes have long necks, to how to solve differential equations, to what I think about my neighbors. Words can make us fall in love, but also go to wars. This ability of language to reflect the inner content of our minds has led Alan Turing to propose his famous test where interacting linguistically with an entity should allow you to disambiguate whether they're a conspecific or a machine. The fact that language often reflects underlying thoughts has resulted in several fallacies in how we think about the relationship between language and thought. One common fallacy is that an entity, a human or a machine, that is good at language must also be good at thinking. If a system is generating coherent stretches of text, it must possess rich knowledge and reasoning capacities. And the rise of large language models has, of course, brought this fallacy to the forefront. These models can produce text that is often hard to distinguish from human output, and as a result, claims have emerged that LLMs represent not only a major advance in language processing, but more broadly in artificial general intelligence, AGI, or a step towards a thinking machine. A different fallacy is that a model that is bad at thinking must also be a bad model of language. So language models are commonly criticized for their lack of consistent generalizable world knowledge, lack of common sense reasoning abilities, and failure to understand what a sentence is really about. According to these critics, the language model's failure to produce linguistic output that fully captures the richness of human thought and its sophistication implies that they're not good models of human language processing. Both of these fallacies stem from the conflation of language and thought, and both can be avoided if we distinguish between the two. So today, first I'm going to talk about the relationship between language and thought in one known system of general intelligence, the human brain. I will present evidence that language and thought are robustly distinct. Next, I'm going to talk about the language-thought distinction in the context of language models and argue that that distinction is important for developing these models, understanding them, and using them as models of human language processing and other capacities. And then finally, I'm going to discuss how we might proceed in both AI and neuroscience, given all this. So let's start with brains. I'll say just a few words about the system in the brain that you're all using at this very moment to understand what I'm saying. We have long known that there's a set of brain areas in the left hemisphere of most people that are important for language. Using brain imaging tools like functional MRI, I can find these regions in your brain in just a 5-minute long data acquisition scan by looking for areas that respond more strongly when you process linguistic input, like listen or read, listen to or read sentences, compared to some condition that is similar perceptually, but doesn't have linguistic meaning and structure. So speech played backwards or listening to speech in a language that's not familiar to you. The language network has a few important properties. So these regions work both when we understand language, and it doesn't matter if it's coming in through our ears when we're listening to someone speak like you're doing right now, or whether we're reading, or if we're watching somebody sign, if we're talking about sign languages. And they are also working during language production. And again, it doesn't matter whether ultimately we're speaking it by moving our mouth, or we're writing it down or typing it on a computer. So these two properties should tell you that the representations that the system operates over are quite abstract. They're not tied to a particular perceptual modality or particular motor system. These regions are broadly sensitive to kind of two key features of language, which is word meanings, knowing what table means, and putting words together into phrases and sentences. So saying, I put the laptop on the computer, put the laptop on the table. And these regions are causally important for language, so that if you damage these regions in adulthood, you're going to have problems with language comprehension and production, or what's known as aphasia. So Together, all of these properties suggest that this is the system in our brains that stores our knowledge of language. This is knowledge that we start acquiring from the moment we're born. A few months in, we start picking up some meanings of words, and then we start saying them around age 1. And we use these representations to both convert our thoughts into sequences of words, so that's encoding, linguistic encoding, and to decode meanings from other people's utterances. That's decoding in comprehension. So now on to language and thought relationships. So what do we mean by thought, or more broadly, cognition? Let's just separate language out for a second and go through some amazing things that we're capable of as humans. We do a lot of cool stuff. We can do things like math. We can engage in logical reasoning. We can engage in totally new, evolutionarily new skills like talking to machines via computer coding. We have a host of executive abilities like attention, working memory, inhibition, as well as planning and decision making. And using all of these abilities, we can solve new problems on totally unfamiliar abstract stimuli. We possess a rich knowledge of the world, of the objects and events that happen. We know about physical constraints on how our world works, and we're socially extremely competent. We can reason what other people think or feel and cooperate with each other in complex ways. So how does language relate to all of these cognitive abilities? It turns out that in human brains, in each of your brains, language is very, very sharply distinct from all of these other capacities. We have two kinds of evidence. How would you know this, right? We have two kinds of evidence for this. One is using brain imaging tools like I mentioned, I can find language areas in any one of your brains and then ask, do these same areas work when you're solving a math problem or when you're reasoning about what somebody else might be feeling or thinking? And using these tools, it turns out that the language system is largely silent when we do all sorts of complex things, including math, logic, computer coding, engaging in demanding executive control tasks, solving problems, understanding the world, understanding events, physical and social reasoning. All of these abilities instead engage distinct areas in your brain that are non-overlapping with the language system. Another approach is to examine thought abilities in individuals who don't have a functioning language system. Some individuals sustain brain damage that effectively wipes out their entire language network. These lesions encompass all of the areas that in healthy individuals, like in all of our brains, support language processing. And we can ask, and these patients have severe linguistic deficits. They cannot understand or produce language. And we can ask, do these patients still have the ability to navigate the world, to imagine what other people are planning and thinking, to do math, and so on? And here the answer turns out to be yes. In spite of these severe linguistic deficits, these globally aphasic individuals, this most severe form of aphasia is called global aphasia, they can nevertheless do all the things that you and I can do, and the only thing that they seem to lack is the ability to convert their thoughts into a verbal format and to extract meaning from verbal utterances. In other words, the encoder-decoder system is gone, but the thoughts are the same as they ever were. So brain imaging evidence and data from patients with language deficits converge to suggest that language and thought are in fact distinct in the human brain. Now, against this backdrop of the language-thought dissociation, I would like to introduce a distinction between what we call formal linguistic competence and functional linguistic competence. So formal linguistic competence can be defined as a set of core capacities to basically produce and understand language. It involves things like knowing what words mean, knowing the rules for putting words together, and knowing all sorts of idiosyncratic regularities in language, like constructions, which are kind of not rule-like, but occur across all languages. And we can contrast this competence in the rules and regularities of language with the ability to use language in real world. When we use language, we can use it to achieve many different things. We can talk about the world, what is true or not. We can discuss highly abstract ideas, turn them into scientific theories, and engage in formal debates. We can make requests, we can perform speech acts, we can joke, we can flatter. And we can construct rich models of the world as we listen to stories or engage in extended conversations. These abilities we refer to as functional linguistic competence. So now if we bring back our picture of language and various other cognitive capacities, we have been arguing that formal competence is enabled by these specialized language regions I mentioned that only work when you produce and understand language, but are silent when you engage in these diverse forms of thought and reasoning. Instead, the functional competence capacities crucially depend on aspects of non-linguistic cognition. And I'm not talking today about brain systems that support these non-linguistic functions, but some of them are quite well characterized in humans and in some cases in animals. So to wrap this section, although language and thought are supported by distinct mechanisms, we routinely use language to send information to and receive information from systems that support different aspects of thought and reasoning. Now, how do things look in language models? So let's first spend a couple of minutes talking about how great language models are, which you guys already spent the morning doing. So language models are incredibly impressive. They're very good at language. They also are similar to the human language system in several ways. At an abstract level, both language models and the human language system are sensitive to the same kinds of information. They're both very sensitive to particular word co-occurring together, as well as to the abstract rules for combining words into phrases and sentences. And they don't have clear segregation between syntactic or structural aspects of language and the meaning aspects of language. Moreover, at a finer grain level, the ways in which language models represent linguistic input is similar to how humans do it, such that if you extract representations from models, they do a good job in capturing brain's responses to linguistic input. How do we find this out? Well, we can do something like this. We can take a sentence, or a few thousand sentences. We can feed a sentence to the model and the same sentence to a human brain. From the model, we extract unit activations, and from the brain, we extract responses as measured with functional MRI or intracranial recordings in some cases. And then, between these two sets of numbers, we compute some similarity metric. So Martin Schrimp, who is now here at EPFL, conducted this work a few years ago, and this result has been found by a few different groups, so this is a robust and replicable finding. So what we did here is using this exact approach I just told you about. We evaluated over 40 models in doing that, in extracting model activations and seeing how well do they capture humans' responses to linguistic input. Each bar here is going to be a model, and on the y-axis is the degree to alignment to the human language system's response. And most of these models, of course, are transformers, the most successful recent models, but there's a few others mixed in there. So here's what we find. The gray line on top shows the upper bound on these correlations. So that means using a different human brain as a predictor model compared to the target brain. So you can't expect an external model to do better than what you can predict, for example, modeling my brain to one of yours. And all the values are normalized by that ceiling. The raw values are on the order of 0.3 or so. Yeah, I said that. But what you can see from this graph is that there are some models whose representations do a really good job at capturing human neural responses to language. So LLMs are good at language. They're similar in many ways to the human language system. What about their ability to think? I would argue that LLMs are really great at pretending to think. In other words, they may create an impression that they're doing something more sophisticated than they actually are. You may have friends or acquaintances like that as well, humans, where they will say things and they sound really fluent, and it sounds like they're saying perfectly well-formed sentences, but if you start deeply thinking about the underlying structure, it's somehow missing. The reason that, of course, we may think that LLMs have learned to think is because language corpora indeed contain a wealth of non-linguistic information that you can pick up from linguistic regularities. Linguistic regularities also capture some aspects of experiential input, as known now from many individual researchers showing pretty good alignment between linguistic representations and visual representations obtained from visual scenes. And so as a result, if a model is trained on massive corpora, it will show to some degree some factual knowledge, perhaps mathematical and logical reasoning abilities. It inherits the same social biases that are present in our society and are reflected in our language. And so broadly, I would say that language models are still limited in their knowledge and reasoning capacities. This knowledge, the world knowledge that they may extract from linguistic regularities is quite brittle. Some of this is getting much better in some more recent models. Typically, when these models have shown more robust reasoning capacities, it has required training on data outside of just language proper. So, for example, a database of code, computer code, or math textbooks, which is not kind of a pure linguistic input. I'll come back to that point in a second. And so based on the current state of affairs, I would conclude that although language models master many syntactic and distributional properties of language, including ones that many linguists have said you just can't learn from the input alone, okay, so that they really have overturned a lot of things that people have been saying for many years. And for that, you don't even need, like GPT-2 already, I think, got us to a level where most of the linguistic regularities are learned really well. But these models, I don't think, quite use language in human-like ways in real life. Right, said that. So where do we go from here? Well, it really depends on where you want to get. And I guess most of you guys are here maybe from industry. And I think keeping this distinction in mind between language processing and thinking is important for both AI and neuroscience. So I've argued that formal and functional linguistic competence are distinct capabilities that recruit distinct sets of brain areas, distinct mechanisms. More broadly, most biological intelligence systems are modular, including both human and non-human minds. And of course, computational advantages of modularity have long been discussed, and there's a vast literature that I can point you, if you're interested, point you to. But what can this modularity tell us about how to build better, more human-like models of intelligence? I think that future language models can master both formal and functional competence if they institute a division of labor between the language component and components for other cognitive processes, such as a formal reasoning component and social reasoning, for example. And again, a few groups are doing that now quite successfully. Now, I'm not saying that this is the only way to do this. At the very least, it's going to be almost certainly more efficient. Right? So instead of just making models larger and throwing more data at them and compute power, I think this approach can potentially get you there faster and maybe in more robust ways. As a neuroscientist, what I'm most excited about is using language models to better understand human brains. I think these models have really revolutionized the field over the last few years, and I think there's exciting things to do. We can think of these models as basically computationally precise hypotheses about how language works. We've been building on the work I mentioned relating model representations to human brains in all sorts of ways, including careful experiments on models to isolate the necessary and sufficient features so that a model captures human brain responses well. We've also been figuring out ways to select or create stimuli that allow us to better differentiate these high-performing models, of which there's quite a few, and they're quite different, but they seem to make similar predictions. So we're trying to figure out how to tease them apart. Or we've also been trying to find kind of the most preferred stimulus of the human language system to try to get insights into the computations that the system is likely carrying out. And we're also building more developmentally plausible models of language to see if those would better align with human brains, because of course, current language models do not learn language in ways that are similar in any way to human kids, both in terms of just getting text as opposed to multimodal inputs, the kinds of content they get, the amount of content they get, and so on. So overall, I think neural networks along with a growing suite of tools for probing the model internals, these models are really no longer just black boxes. I think that's just no longer true. We have really good tools for trying to understand what's going on inside these models. I think these models can help us make serious strides in understanding how our brains achieve remarkable feats like language, and perhaps by building multi-componential models, we can also begin probing intersystem interactions, like how does a language system interact with our system of world knowledge to achieve things in the world. And for these kinds of questions, we currently don't have great tools in neuroscience, so this may be a place where models are uniquely suited to help us understand those interactions and kind of model uniquely human cognition as a whole. Thank you very much for listening.
Thank you, Ev, for a wonderful talk. And we can take questions from the audience now.
Bring them.
Hi, you mentioned modularity in the brain. So one of the things I've read basically is functional versus system modularity. So like, is the circuit actually separate or not? And how do you basically think about reconciling that kind of ambiguity in neural networks?
Are you asking in the models?
Correct.
Right?
I mean, so like
Yeah.
we don't exactly know that one part of the brain exactly is just doing this, right? So it's more functional modularity than circuit modularity, where different parts of the brain are absolutely doing different things. And so when it comes to functional modularity, how do we reconcile that in neural networks?
I don't know what you mean by reconcile. I mean, modularity in networks, you can either build it in, or you can see if it emerges naturally, right? So that's certainly a very different kind of thing. And a lot of people are now probing to see if some kind of specializations emerge for different aspects of language, or for language versus other things, especially if you're training on different kinds of data. So I'm not sure I quite get what you mean by reconcile.
I mean, so yeah. You kind of answered my question. Basically, what I mean to ask is, because we don't exactly know if there's a separation.
That's right.
How exactly do we actually like work?
So we can use some of the tools from neuroscience to actually probe for selectivity, right? And people like Robert Yang have been doing it in RNN, recurrent neural networks, for example, complex executive tasks. And we're actually trying to do that now in models that are trained on language and other kinds of input like math, to try to see if a natural separation happens just by virtue of training on these.
Thank you. Thank you so much for the talk.
Yeah.
I wonder if I could ask a question while the mic's going out.
Sure. Go ahead.
I had a question about the lesion data you mentioned, I think, which are very powerful. And then I'm wondering about a comment you said right at the end about looking at how humans naturally acquire language in a developmental context. Don't the brains that get lesioned that you're referring to, didn't they already spend many years developing language systems before the lesion? How do you...
That's right. That's a very good question. So that's absolutely right. So what those data tell you is that once all the capacities are in place, you can take the encoder-decoder away and you can still reason. Now, this still contradicts many, many claims about how linguistic representations are the very medium of complex thought, so it does rule this out. The question of whether you need language to develop the kinds of brains we have is a hard question to test. Can't deprive kids of language. There are some natural experiments. So oftentimes, the majority of deaf kids are born to hearing parents. And in some circumstances, such kids sometimes don't get linguistic input for the first few years, sometimes well into their teenage years, because they can't hear speech, and their parents will typically not have had a reason to learn sign language, so they're not getting sign language input. And you can ask, do these kids grow up reasoning in similar ways to kids who get linguistic input? And the data there are sparse, but it doesn't seem like they lack fundamental ability to build complex causal chains, to make generalizations, abstractions. But I think there is a lot of interesting work to potentially do in that population, since it still exists.
So we can take one more question. Yeah.
Here, I have the microphone. Can I ask? Up here. So, here on the left. So, thank you very much. Very, very interesting talk. I have one question. You showed very nicely how how you can use neurons activations in transformers to predict brain activation for language. And so you said, so your conclusion is that the language models, they can learn language, but then you said it cannot predict cognition, right? But do you have evidence on that, or how would you build that evidence? I mean, showing that neural networks activations cannot really predict cognitive areas of the brain.
Yeah, if I said I didn't, we haven't tested that. I hope we can test this, especially in models that show impressive reasoning capacities like some of the later models. As of right now, I don't think the right neural data quite exists, so I didn't mean to imply that the current models cannot capture those things. There I was just focusing that with respect to language responses, these models do a good job, so there's some similarities in how they represent linguistic input, but I do very much hope that some of our ongoing work where we're building these componential models with a language component and some component of human some component of cognition, we can then try to see if these different components, for example, capture responses in different parts of the brain, in different systems, as well as trying to understand, like, how do linguistic representations have to transform so that some downstream reasoning system can use those representations to do things like, get you to the next state, whatever you're trying to do.